Good afternoon everybody. I welcome all of you to eGuru CET coaching classes physics. Today I will discuss some important questions about thermal properties of matter and thermodynamics. I am Gauri from Government PU College, Sanur. Today let us study about these important questions. Let us see the first question. 200 gram of solid ball at 20 degrees Celsius is dropped in an equal amount of water at 80 degrees Celsius. The resulting temperature is 60 degrees Celsius. This means that specific heat of solid is. Here, this question is based on the concept of specific heat, that is heat capacity. We have heat capacity S is the ratio of delta Q by delta T. When we supply heat energy to a system, its temperature increases. We know that heat is a form of energy. When heat is given to a system, temperature increases. Say delta Q is the amount of heat supplied to the system, and delta T is the increase in temperature of the system. The increase in temperature is directly proportional to the amount of heat supplied to the system. The amount of heat supplied also depends on the mass of the system, or delta Q, the amount of heat supplied, is proportional to M into delta T. Removing the proportionality sign, we get delta Q is equal to, say, S into M into delta T, where S is called specific heat capacity. Heat capacity and specific heat capacity. Say S is specific heat capacity. It is defined as the amount of heat required to raise the temperature of 1 kg of substance by 1 Kelvin. 1 kg ಸಬ್ಸ್ಟೆನ್ಸ್ ಅನ್ನು 1 ಡಿಗ್ರಿಯಷ್ಟು ಟೆಂಪರೇಚರಲ್ಲಿ ಇನ್ಕ್ರೀಸ್ ಮಾಡಬೇಕಾದ್ರೆ ಎಷ್ಟು ಅಮೌಂಟ್ ಆಫ್ ಹೀಟ್ ಸಪ್ಲೈ ಮಾಡಬೇಕು ಅನ್ನೋದನ್ನು ಸ್ಪೆಸಿಫಿಕ್ ಹೀಟ್ ಕೆಪಾಸಿಟಿ ಅಂತ ಹೇಳ್ತೇವೆ. ಸೇ ವಿ ಹ್ಯಾವ್ ದಿಸ್ ಇಕ್ವೇಷನ್ ಡೆಲ್ಟಾ ಕ್ಯೂ ಇಸ್ ಈಕ್ವಲ್ ಟು ಎಮ್ ಎಸ್ ಇಂಟು ಡೆಲ್ಟಾ ಟಿ. ಯೂಸಿಂಗ್ ದಿಸ್ ಕಾನ್ಸೆಪ್ಟ್ ವಿ ಕ್ಯಾನ್ ಸಾಲ್ವ್ ದಿಸ್ ಪ್ರಾಬ್ಲಮ್. ಹಿಯರ್ 200 ಗ್ರಾಮ್ ಆಫ್ ಸಾಲಿಡ್ ಬಾಲ್ at 20 degrees Celsius is dropped into an equal amount of water. That means from the question we get M1 is equal to M2. Initial temperature of the solid ball. Let T1 be the initial temperature of the solid ball. This is 20 degrees Celsius. Is dropped into an equal amount of water at 80 degrees Celsius. Let T2 be temperature of water, T1 be temperature of the solid. The resulting temperature, when they are mixed together, when two substances at two different temperatures are mixed together, hot body loses the heat energy and cold body gains the heat energy. Until equilibrium, thermal equilibrium is reached, heat transfer takes place. ಯಾವಾಗ ಟೆಂಪರೇಚರಲ್ಲಿ ಈಕ್ವಲಿಬ್ರಿಯಮ್ ಬರ್ತದೆ ಅಲ್ಲಿ ತನಕ ಹಾಟ್ ಬಾಡಿ ಲೂಸಸ್ ದ ಹೀಟ್ ಎನರ್ಜಿ, ಕೋಲ್ಡ್ ಬಾಡಿ ಗೇನ್ಸ್ ದ ಹೀಟ್ ಎನರ್ಜಿ. ಲೆಟ್ ಟಿ ಬಿ ದ ಟೆಂಪರೇಚರ್ ಆಫ್ ದ ಮಿಕ್ಸ್ಚರ್ ಆ್ಯಂಡ್ ಇಟ್ ಈಸ್ ಗಿವನ್ ಟೆಂಪರೇಚರ್ ಆಫ್ ದ ಮಿಕ್ಸ್ಚರ್ ಈಸ್ 60 degrees Celsius. That is heat lost by the hot body. Say M1S1 into temperature difference between heat absorbed is equal to heat lost, temperature of the cold body. Cold body absorbs the heat energy, temperature is increased in the cold body. T minus T1 is the increase in temperature of the cold body, which is equal to M2S2 into T2 minus T, where T2 minus T is the heat lost by the hot body. Temperature, decrease in temperature of the hot body. It is given M1 is equal to M2, therefore we can cancel M1 and M2 on both sides. Or S1 into T1 minus T1. T is 60 degree, temperature of the mixture is 60 degrees Celsius. temperature of the cold body is 20 degrees Celsius is equal to S2 into temperature of the hot body is 80 degrees Celsius minus temperature of the cold body. Mixture is 60 degree Celsius. Rearrange the equation, calculate S1. S1 is equal to S2 into 80 minus 60 is 20 divided by 60 minus 20, that is 40. Or this is equal to, cancel this, we have S2 by 2. S1 is equal to S2 by 2. Our option, we have 4 options. Specific heat of solid, specific heat of the first body S1 is equal to 1/4 of water, 1/2 of water, twice of water and 4 times of water. S1 is the specific heat of the solid ball, S2 is the specific heat of water. From the solution we get specific heat of solid is 1/2 of specific heat of water. This is the first question. Let us go to the next question. Two liquids at temperatures 20 degrees Celsius and 40 degrees Celsius. When the same mass of both of them is mixed, temperature of the mixture is 32 degrees Celsius. What is the ratio of specific heats? Here again, this question is similar to previous question. ನಾವು ಈಗಷ್ಟೇ ಡಿಸ್ಕಸ್ ಮಾಡಿದ ಕ್ವಶನ್ ಸಿಮಿಲರ್ ಪ್ಯಾಟರ್ನಲ್ಲಿ ಈ ಕ್ವಶನ್ ಇದೆ. Two liquids are at temperatures, say T1 is the temperature of the first body 20 degrees Celsius, T2 be the temperature of the second body 40 degrees Celsius. When mass of both of them is mixed, M1 is equal to M2. Temperature of the mixture, let T be the temperature of the mixture, this is equal to 32 degree Celsius. What is the ratio of specific heats? Let S1 be the specific heat of the first body, S2 be the specific heat of the second liquid. We were asked to calculate S1 by S2. Using the same pattern as in previous case, heat lost by the hot body is equal to heat gained by the cold body when there is no loss of heat. Heat lost by the hot body and heat gained by the cold body are equal in magnitude. That is, heat lost M1 S1 into T minus T1 is equal to heat absorbed by the cold body is equal to heat lost by the hot body. M1 and M2 are equal. Cancel these two. S1 into T minus T1, where T is the temperature of the mixture, 32 minus 20 is equal to S2 into T2 minus T. T2 is 40 minus T. T is 32. The ratio of specific heats is rearrange the equation. S1 by S2 is 40 minus 32, 8. 32 minus 20 divided by cross multiply, this is 12, which is equal to 2 by 3. The ratio of specific heat is 2 by 3. We have the option 1 by 3, 2 by 5, 3 by 2 and 2 by 3. The option D is correct. Let us move on to the next question. Two metal rods A and B of equal length and cross-sectional area are joined end to end. The coefficient of thermal conductivity of A and B are in the ratio 2:3. When the free end of A is maintained at 100 degrees Celsius and free end of B is maintained at 0 degrees Celsius, then temperature of the junction is. See, according to the question, two metal rods A and B of equal length, L1 is equal to L2. They are connected end to end. They have equal length and equal cross-sectional area. L1 is equal to L2 and A1 is equal to A2. Thermal conductivity of A and B are in the ratio. The ratio of thermal conductivity of two bodies are given by K1 by K2 is equal to 2:3. When the free end, say first body is A, second body is B. Free end of A is maintained at 100 degrees Celsius and free end of B is maintained at 0 degrees Celsius. What is the temperature of the junction? You are asked to calculate temperature of the junction. To solve this problem, we use the method of mode of transfer of heat. There are three different modes of transfer of heat: conduction, convection and radiation. Conduction is the method of transfer of heat in solids. We use the equation rate of flow of heat in solids, rate of flow of heat, or this is also called heat current. This depends on area of cross section, directly depends on temperature difference between hot end and cold end, and inversely proportional to distance between hot end and cold end. Or dq by dt is equal to Ka into Th minus Tc by L, where Th is the temperature of hot body, Tc is the temperature of cold end. L is the distance between hot end and cold end. Where K is the proportionality constant, this is called coefficient of thermal conductivity, and A is area of cross section. From the figure, two bodies of different material. Here thermal conductivity depends on material. It is different for different materials. Different materials are connected end to end, and the free ends of A and B are kept at two different temperatures. They have equal area of cross section and equal length. L1 is equal to L2, A1 is equal to A2, and thermal conductivity of A and B are in the ratio 2:3. We have, using this equation, dq by dt is equal to Ka into Th minus Tc by L. Let us consider the first part. First conductor A, first rod A, apply this dq is by dt is equal to K1A, temperature of hot end 100 degrees Celsius, minus temperature of cold end is T, junction is T. Here we can understand that heat flows from hot body to cold body. Heat flows from 100 degrees Celsius to 0 degrees Celsius in this direction. Therefore, T, temperature of T junction is less than 100 degrees Celsius divided by L. At steady state, the rate of flow of heat is same. Therefore, this is equal to K2 into A into Th, temperature of hot body. For the second body, T is hot compared to end C. Say this point is at 0 degrees Celsius, this is at higher, junction is at higher temperature, say T. Therefore, T minus 0 degrees Celsius divided by L. Now, if you cancel L on both sides and A on both sides, since they are equal, we get K1 into 100 minus T is equal to K2 into T. Rearrange the equation. K1 by K2 is equal to T by 100 minus T. But K1 by K2 is given, it is 2 by 3. 2 by 3 is T by 100 minus T. Cross multiply, we get 2 into 100 minus T is equal to 3T. Rearrange the equation, open the bracket, we get 200 is equal to 5T, or T is equal to 200 divided by 5, that is 40 degrees Celsius. Temperature of the junction is 40 degrees Celsius. We have four options: 30 degrees Celsius, 40 degrees Celsius, 50 degrees Celsius and 60 degrees Celsius. Option B is correct. Let us go to the next question. Two metal plates of same thickness, coefficient of thermal conductivity K1 and K2, and area of cross sections A1 and A2 are connected as shown in the figure. The common coefficient of thermal conductivity will be, say in the figure it is given length or distance between two ends is same. Two materials are different area of cross section and thermal conductivities are also different. Two different materials are arranged in this pattern. You are asked to calculate total thermal common coefficient of thermal conductivity. So we have, using the previous concept, using the rate of flow of heat in conduction is directly proportional to area of cross section and directly proportional to temperature difference between hot end and cold end, inversely proportional to distance between hot end and cold end, or dq by dt is equal to Ka into Th minus Tc by L. Using this equation we can solve this problem. Say common rate of flow of heat. If you consider two bodies together, then let K be the common thermal conductivity. K be the common thermal conductivity of two materials. A is the area of cross section. Here A1 is the area of cross section of the first body. A2 is the area of cross section of the second material. Therefore, A1 plus A2 be the area of cross section of two bodies together. When we consider the two materials together, total area of cross section is A1 plus A2 into temperature of hot end minus cold end. Temperature is not given in this equation. Let us write it as it is, divided by the separation between hot end and cold end. This is L. This is also equal to common rate of flow of heat is equal to rate of flow of heat due to first conductor plus rate of flow of heat due to second metal conductor. dq1 by dt, K into K1 is the area of cross section, K1 is the thermal conductivity of the first body, A1 is the thermal area of cross section of the first body, T1 Th minus Tc is the temperature difference between hot end and cold end, divided by length L plus dq2 by dt. For the second body, it is K2A2 into Th minus Tc divided by L. From this equation, we can cancel some of the common terms. Here L is common. Take L outside the bracket. Th minus Tc is also common. Th minus Tc, temperature difference between hot end and cold end. Take these two terms outside the bracket. K1A1 plus K2A2. In the LHS we have K into A1 plus A2 into Th minus Tc divided by L. Cancel the common terms. We get K into A1 plus A2 is equal to K1A1 plus K2A2, or K is equal to the common thermal conductivity. K is equal to K1A1 plus K2A2 divided by A1 plus A2. Say first option is K1A1 plus K2A2, second option K1A1 plus K2 divided by K2A2, third option K1A1 plus K2A2 divided by A1 plus A2. This is the right answer. Option C is correct. Next, let us go to the next question. Question number 5. Two metallic rods of same length, same material, same area of cross section, same length, same material, same area of cross section. That means K1 is equal to K2, A1 is equal to A2 and L1 is equal to L2 are connected first in series and then in parallel. The thermal conductivity of the combination would be, what is the thermal conductivity of the combination of series combination? what is the thermal conductivity of a parallel combination? Option A, 2k k by 2, k by 2 comma 2k, k comma k, 2k comma 2k. Here option C is correct because thermal conductivity depends on the material and not the combination. The combination may be series or parallel. It does not mean that thermal conductivity depends only on the material. Rate of flow of heat depends on the material. Option C is correct. Let us go to the next question. A black body radiates at two temperatures T1 and T2 such that T1 is less than T2. The frequency corresponding to maximum intensity. Black body. Here this concept of black body. A black body which absorbs all the radiations incident on it is called black body. Body which absorbs all the radiations incident on it. 100% absorption is possible. Only such bodies are called black bodies. There is no radiation, there is no reflection and there is no transmission. When this black body is maintained at two different temperatures, radiates at two different temperatures such that T1 is less than T2, the frequency corresponding to maximum intensity is. Say the plot of black body emits radiation, the plot of energy of emitted radiation with wavelength lambda for different temperatures is obtained as shown in the figure in this graph. Say this is a continuous curve that represents energy emitted is continuous and not of particular wavelength. At lower temperature, say 2000 Kelvin, as temperature increases, say 3000 Kelvin, 4000 Kelvin. And one more point we can observe here is, the graph is a continuous curve and there is one peak point in each graph. Energy of emitted radiation is maximum at one particular point. This particular wavelength is called lambda m for first graph, which is at temperature 2000 Kelvin. For the second graph, if you observe, there is again peak point, energy emitted is maximum. This is another temperature called lambda m. And for the third graph also, as temperature increases, the energy emitted corresponding to maximum temperature, maximum energy for the wavelength, we can observe from the graph, it is not at the same point. Lambda m corresponds to is the wavelength corresponding to maximum energy. As temperature increases, lambda m is shifted towards a shorter wavelength. As temperature increases, lambda m is shifted towards a shorter wavelength means lambda m is inversely proportional to temperature T. But lambda and frequency, wavelength and frequency are related. We have the relation nu is equal to C by lambda, that is nu is inversely proportional to lambda. Since lambda m is inversely proportional to T, lambda m is also inversely proportional to nu, or frequency is directly proportional to temperature. Nu1 is directly proportional to T1, nu2 is lambda T2, or lambda m is maximum for shorter wavelength, nu is minimum for shorter wavelength, or nu2 is greater nu2 is greater than nu1. Answer option, it is less at T1, less at T1. As temperature increases, lambda m decreases. Lambda m is inversely proportional to frequency, or for lower temperature lambda 1, higher temperature lambda 2, or lambda nu1 is less than nu2. Option less at T1. First option is correct. A piece of iron is heated in a flame. It becomes dull red and then becomes reddish yellow and finally turns to white hot. The correct explanation of the above observation is possible. Just now we have discussed black body radiation, the energy of emitted during black body radiation versus wavelength. The plot of graph at different temperatures is obtained like this. This is at 2000 Kelvin, say 3000 Kelvin and 4000 Kelvin. As the temperature increases, the peak value is shifted towards shorter wavelength region. Lambda m is inversely proportional to temperature, or lambda m into T is constant. We have this explanation for black body. This is called Wien's displacement law. In the given problem, a piece of iron is heated in a flame. When we supply heat energy to a system, we know that temperature increases. When we supply heat energy, temperature increases. It becomes dull red, then becomes a reddish yellow. Dull red, then becomes a reddish yellow, and then becomes a white hot. So we have the wavelength for these colors. According to this, violet, indigo, blue are the low wavelength region, and yellow, orange, red are the high wavelength colors. When the heat energy is given to a system, the color changes from yellow or red to yellow and then to white. White means it is the at least two minimum colors, minimum of two colors, 400 nanometer and 500 nanometer combined together, and they appear as white. As temperature increases, the wavelength decreases. Temperature and wavelength are inversely related using this equation that is called Wien's displacement law. This statement is called Wien's displacement law, and the correct answer is option 3. A faulty thermometer has its fixed points marked 5 and 95. Faulty thermometer ಅಂದರೆ ಥರ್ಮೋಮೀಟರಲ್ಲಿ ಡ್ಯಾಮೇಜ್ ಇದೆ. ಡ್ಯಾಮೇಜ್ ಇರುವ ಥರ್ಮೋಮೀಟರಲ್ಲಿ ಮಿನಿಮಮ್ ರೀಡಿಂಗ್ 5 ಇದೆ ಆ್ಯಂಡ್ ಮ್ಯಾಕ್ಸಿಮಮ್ ಪಾಯಿಂಟ್ 95. When the thermometer reads 68, the correct temperature in degrees Celsius is. This question is based on the concept of heat and temperature. Temperature, when we supply the heat energy to a system, its temperature increases. We use a thermometer to measure the temperature. There are different scales of thermometer. To convert one scale to another scale, we have some common terms. The equation is reading at any condition, reading at any temperature minus lower fixed point divided by upper fixed point minus lower fixed point. ಈ ಇಕ್ವೇಷನ್ ಅನ್ನು ಯೂಸ್ ಮಾಡಿಕೊಂಡು ನಾವು ಯಾವುದೇ ಸ್ಕೇಲನ್ನು ಒಂದರಿಂದ ಇನ್ನೊಂದು, ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ಡಿಗ್ರಿ ಸೆಲ್ಸಿಯಸ್ ಟು ಫ್ಯಾರನ್ಹೀಟ್, ವಿ ಕ್ಯಾನ್ ಕನ್ವರ್ಟ್ ಒನ್ ಸ್ಕೇಲ್ ಆಫ್ ಟೆಂಪರೇಚರ್ ಟು ಅದರ್ ಸ್ಕೇಲ್. ಹಿಯರ್ ರೀಡಿಂಗ್ ಎಟ್ ಎನಿ ಟೆಂಪರೇಚರ್, a faulty thermometer points, say the thermometer reads 68 degree, 68 minus lower fixed point is 5 divided by upper fixed point is given, it is 95 minus lower fixed point, it is 5, which is equal to, our aim is to convert it to temperature in Celsius scale. For Celsius scale, temperature is not known, we have to convert it, minus lower fixed point is, the lowest possible temperature in Celsius scale, thermometer in Celsius is 0 degree Celsius, and upper limit is 100 degree Celsius and lower limit is 0 degree Celsius. To simplify this equation, 68 minus 65, that is 63 divided by 95 minus 90 is equal to T minus 0 divided by 100 minus 0. Cross multiply or simplify, we can divide by 9. 9 sevens are 9 tens is equal to t by 100. Cross multiply, 700 divided by 10 is equal to t, or t is equal to 70 degrees Celsius. This is how we can convert any scale of temperature to any other scale. Fahrenheit in the degree Celsius ge convert madudu same. Degree Celsius scale in the Fahrenheit ge, Celsius in the Fahrenheit ge convert madudu, we use the same method. Next question, the coefficient of performance of a refrigerator. Coefficient of performance of a refrigerator. You know what is a refrigerator? Heat engine and refrigerator. Heat engine is a device used to convert heat into mechanical work. Refrigerator is the reverse of heat engine. Here we have three systems: source, hot body, which is at high temperature, working substance, and cold body. This is also called sink. Refrigerator is the reverse of heat engine. Refrigerator absorbs heat from the working substance, absorbs heat from the cold body, and some amount of work is done on the working substance, rejects the heat into hot body. The coefficient of performance of a refrigerator is given by the equation T2 by T1 minus T2. T2 divided by T1 minus T2. Here T2 is the temperature of the cold body. Cold body is maintained at 10 degrees Celsius. 10 degrees Celsius, convert it into Kelvin scale. We can convert degree Celsius to Kelvin scale by adding 273. Now this is 283 Kelvin. Temperature of the hot body is 20 degrees Celsius, which is equal to 273 plus 20, 293 Kelvin. Therefore, coefficient of performance of the refrigerator is T2 divided by T1 minus T2. T2 is 283, T1 minus T2, 293 minus 283, which is equal to 283 divided by 10, or 28.3 is a correct answer. Option A is correct. If pressure and temperature of an ideal gas are doubled. Next question is, if pressure and temperature of an ideal gas are doubled and volume is halved. Pressure and temperature of an ideal gas. It is given ideal gas. We have the ideal gas equation PV is equal to nRT. What is an ideal gas? A gas which obeys Charles' law and Boyle's law at all conditions is called an ideal gas. The equation for an ideal gas is PV is equal to nRT. It is given pressure and temperature are doubled. P2 is equal to 2P1. Temperature T2 is equal to 2T1 and volume is halved, V1 by 2. The number of moles of gas. PV is equal to nRT. R is universal gas constant, P is pressure, V is volume, and T is the temperature. Or we can also rearrange this equation. PV is proportional to N into T, or N is proportional to PV by T. As pressure is doubled, N is proportional to 2P, volume is halved, temperature is also doubled. 2 cancels, N is proportional to PV by T into half, or PV by T is initial temperature, initial condition, PV by T is initial condition, new number of moles is half of initial condition, it becomes half. it becomes half. Next, question number 11. The ratio of thermal conductivity of two rods of different materials is 5:4. Two rods of same area of cross section and same thermal resistance will have length in the ratio. To the ratio of thermal conductivity, we use the word K for thermal conductivity. Thermal conductivity of two rods K1 is to K2 is given by 5:4. The two rods of same area of cross section A1 is equal to A2. Thermal resistance also same, R1 is equal to R2. Will have length in the ratio. You are asked to calculate L1 by L2. Now we have rate of flow of heat. This question is based on the concept of conductivity, conduction. Rate of flow of heat is equal to Ka into Th minus Tc by L, as discussed in the previous problems. Rate of flow of heat in conduction is equal to Ka, where K is a coefficient of thermal conductivity, A area of cross section, Th temperature of hot end, Tc temperature of cold end, and L is separation between hot end and cold end. Ka into Th minus Tc by L. Thermal resistance is defined as the ratio of change in difference in temperature divided by dQ by dt, which is equal to L by Ka. Here in the equation we get this as L by Ka. But it is given R1 is equal to R2. Thermal resistance is same. Area of cross sections also same. Calculate L1 by L2. R1 is equal to R2 means R is L by Ka. L1 divided by R1 is equal to R2 implies L1 by K1A is equal to L2 by K2A. Rearrange the equation. L1 by L2 is equal to K1 by K2. But K1 by K2 is given. K1 by K2 is 5:4. Therefore, L1 is to L2 is also equal to 5:4. Option number A. Option A is the right answer. Next, let us go to the next question. An ideal monoatomic gas is around the cycle ABCDA as shown in P versus V diagram, PV diagram, pressure volume diagram. The work done during the cycle is, say for the complete cycle in a PV diagram, the area under PV graph gives the work done. Area under PV graph is the work done. Because work done is given by PdV. Work done, we know this as a pressure. P is pressure, V is a volume. Shape of a graph is a rectangle. Area of rectangle is length into breadth. Therefore, this is length is 2V minus V, that is V. Breadth is 2P minus P. P into V. This is the right answer. Option A is correct. Let us move to the next question. In the indicator diagram, the net amount of work done will be. Again, this is similar to the previous question, PV diagram, but the loops here, the shape of the graph is a loop. There are two loops are given. The two loops are of different sizes. and you can observe the arrow marks here. One is clockwise and the other one is anti-clockwise. We have two different directions. Say for the complete cycle, clockwise is taken as positive and anti-clockwise direction is taken as a negative. Clockwise direction is taken as positive and anti-clockwise direction is taken as a negative. Loop 1 is anti-clockwise. Therefore, it is negative, and loop 2 is clockwise and it is positive. Now, if you add the net work done in these two cases, positive value is greater than negative value, or net result is a positive quantity. Therefore, the option A is correct. Net value work done will be positive. Let us go to the next question. Next question is based on thermodynamics. If 110 joule of heat is added to a gaseous system, it acquires internal energy of 40 joule. Then amount of work done will be. Here this question, we have 110 joule of heat energy. We have the symbol dq for heat energy. dq is 110 joule. 110 joule of heat energy is added to a system and it acquires internal energy. We have the used symbol U for internal energy. Internal energy increases by 40. Then the amount of work done will be. From the first law of thermodynamics, we have dq is du plus dw. dq is the amount of heat given to the system. du is increase in internal energy and dw is the amount of work done by the system. dq is du plus dw. You are asked to calculate work done. dw is dq minus du. dq minus du. dq is 110 minus du 40, or this is equal to 70 joule. Option B is correct. The efficiency of next question is question number 15, that is efficiency of a Carnot engine working between 800 Kelvin and 500 Kelvin is. Carnot engine, efficiency of Carnot engine is defined as the ratio of amount of work done to the amount of heat absorbed. Work done is W2 minus W1. Amount of heat absorbed is, Q2 minus Q1 minus Q2 is the amount of work done. Heat absorbed is Q1, where Q1 is the amount of heat absorbed from the source, which is at hot body, and Q2 is the amount of heat rejected to the sink. This is also equal to 1 minus T2 by T1. The T1, given equation, T1 is 800 Kelvin and T2 is 500 Kelvin. Substituting the value, we get equation for efficiency is 1 minus 500 by 800, or this is equal to 1 minus 5 by 8. 5 by 8 is 0.6 to 5, or the correct answer is 0.375. Option C is correct. Next, let us go to the next question. That is question number 16. A pan filled with hot food cools from 94 degrees Celsius to 86 degrees Celsius in 2 minutes. When the temperature of room temperature is 20 degrees Celsius, how long it will take to cool from 74 degrees Celsius to 66 degrees Celsius? So it is given a pan filled with hot food. It cools. Cools andre thermal radiations are emitted from this. Initial temperature is 94 degrees Celsius. It cools to 80 degrees Celsius, 86 degrees Celsius. Time taken is 2 minutes. And the surrounding temperature is 20 degrees Celsius. This question is based on the concept of Newton's law of cooling. According to the statement, Newton's law of cooling, rate of cooling is proportional to temperature difference between hot system and surrounding. When the temperature difference between system and surrounding is more, cooling is faster. When the temperature difference between system and surrounding is less, cooling is slower. That is, T1 is the initial temperature of the system, 94 degrees Celsius. T2, it reduces to 86 degrees Celsius in 2 minutes. First find the rate of cooling. dQ by dt is equal to minus Ka into K into T2 minus T1. Say rate of cooling. Calculate ಮಾಡುವಾಗ final temperature of the system minus initial temperature final temperature is 86 degrees Celsius, initial temperature is 94 degrees Celsius, divided by time taken to cool from say 94 to 86 degrees Celsius is 2 minutes. This rate of cooling is equal to K into temperature difference between system and surrounding. Here temperature of the system, 94 is the initial temperature and 86 is the final temperature of the system. Average temperature we have to consider. So there is temperature difference between the system at same time, or average temperature is 94 plus 86 divided by 2 is the average temperature of the system. This is equal to 90 degrees Celsius. 94 plus 6 divided by 86 plus divided by 2. Average temperature is 90 degrees Celsius minus temperature of the surrounding. Surrounding temperature is 20 degrees Celsius. 86 minus 94 minus 8 by 2 is equal to minus K into 90 minus 20, which is equal to 70. This is about the first system. And you are asked to calculate how long it will take to cool from 74 degrees Celsius to 66 degrees Celsius. 94 ಡಿಗ್ರಿ ಸೆಲ್ಸಿಯಸ್ಸಿಂದ 86 ಡಿಗ್ರಿ ಸೆಲ್ಸಿಯಸ್ ಬರಲಿಕ್ಕೆ 2 ನಿಮಿಷ ತಗೊಂಡಿದ್ರೆ 74 ಡಿಗ್ರಿ ಸೆಲ್ಸಿಯಸ್ಸಿಂದ 66 ಡಿಗ್ರಿ ಸೆಲ್ಸಿಯಸ್ ಬರಲಿಕ್ಕೆ ಎಷ್ಟು ಟೈಮ್ ತಗೊಳ್ತದೆ? ಫಾರ್ ದ ಸೆಕೆಂಡ್ ಕೇಸ್ Initial temperature is 74 degrees Celsius. Final temperature is T2 final temperature is 66 degree Celsius. How long it will take? What is the time taken? ಈ T ಅನ್ನು ನಾವು ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಬೇಕು. To calculate the T, we use the equation rate of flow of heat. Again use the same law, Newton's law of cooling. dq by dt for the second case is equal to final temperature minus initial temperature divided by time taken is equal to minus k into temperature difference between system and surrounding. Temperature of the system is the average temperature of these two. This is equal to 70 minus 22 divided. We have two equations, equation 1 and equation 2. This is again equal to 8 by T is equal to minus K into 20, not 22, 20, 50. Equation 1 divided by equation 2 gives minus 8 by 2 is equal to minus k into 70 divided by minus 8 by t divided by minus k into 50. Cancelling k on both sides, negative also cancels, cancel 8 on both sides. This is equal to t by 2 is equal to 7 by 5. Cross multiply, we get 14 by 5. 14 by 5 is nearly 2.8 minutes. The time taken to cool from 74 degrees Celsius to 66 degrees Celsius is 2.8 minutes. The option B is the correct answer. Repeat, a pan filled with hot food cools from 94 degrees Celsius to 86 degrees Celsius. 94 degrees Celsius ಇಂದ 86 degrees Celsius ತನಕ ಬರಲಿಕ್ಕೆ 2 ನಿಮಿಷ ಟೈಮ್ ತಗೊಂಡ್ರೆ ವಾಟ್ ಈಸ್ ದ ಟೈಮ್ ಟೇಕನ್ ಟು ಕೂಲ್ ಫ್ರಮ್ 74 degrees Celsius to 66 degrees Celsius. ಇಲ್ಲಿಂದ ಇಷ್ಟು ಡಿಗ್ರಿ ಟೆಂಪರೇಚರ್ ಡಿಫರೆನ್ಸ್ ಈಸ್ ಸೇಮ್ ಇನ್ ಬೋತ್ ಕೇಸಸ್. ಇನ್ ದ ಫಸ್ಟ್ ಕೇಸ್ ಟೆಂಪರೇಚರ್ ಡಿಫರೆನ್ಸ್ ಈಸ್ 8 degrees Celsius. In the second case is also temperature difference is 8 degrees Celsius. First case alli 2 minutes ತಗೊಂಡ್ರೆ second case alli ಎಷ್ಟು time ತಗೊಳ್ತದೆ? This is the question. To solve this we use Newton's law of cooling. According to Newton's law of cooling, as the rate of cooling is proportional to temperature difference between system and surrounding. That is, if the temperature difference between system and surrounding is more, cooling is faster. When the rate difference between system and surrounding is less, cooling becomes slower. Rate of cooling is proportional to Ka. dq by dt is equal to minus into K T2 minus T1. For the first case, we have this, on simplifying we get this equation, and for the second case T is unknown and we get the equation like this. Now equation 1 divided by equation 2 gives the final answer. Time taken to cool from 74 degrees Celsius to 66 degrees Celsius is 2.8 minutes. It is clear from this equation, cooling becomes slower when the temperature difference is less. Let us go to the next question. 4 rods with different radii and length L are used to connect 2 heat reservoirs at 2 different temperatures. which one will conduct more? In this question is based on thermal conductivity. To study this question, consider a rod connected between two reservoirs which are at two different temperature. T1 is the hot reservoir and T2 be the cold reservoir. Let us consider this. Rate of flow of heat. Which one will conduct more heat? dq by dt. dq by dt, as we have discussed in the previous questions, is equal to Ka into temperature difference between hot end and cold end and inversely proportional to length L. Here, radius of cross section are given, length L is also given, area is not given. Radius is given means we can calculate the area. The equation becomes A is equal to pi r square is the area of circular cross section divided by L into temperature difference between hot end and cold end. Or here K is a thermal conductivity, pi is constant, r square by L varies, and temperature of hot end and cold end are kept at the same condition. From this equation it is clear that if we vary the length and radius of curvature, the rate of cooling varies. Rate of cooling depends on r square by L. dq by dt proportional to r square by L. Using this equation, let us analyze all these options. For the first option, rate of cooling is r square by L. R square 1 centimeter divided by L 1, 10 to power raised to minus 4 divided by 1, 10 power raised to minus 4 meter. Then second option, r square by L. R square 10 power raised to minus 2 square divided by L 0.5, 10 power raised to minus 4 by 0.5, 0.5 or this is equal to 2 into 10 power raised to minus 4. Third option, r square by L 2 into 10 power raised to minus 2 square divided by L is equal to, cancelling 2 we get 2 into 10 power raised to minus 4. And fourth option, r is 2 centimeter, L is 0.5. R square by L 2 into 10 power raised to minus 2 square divided by L 0.5. 0.5 is 1 by 2, 1 by 2 it becomes 4 into 10 power raised to minus 4 into 2. Denominator na denominator allide, it goes to the numerator, or 8 into 10 power raised to minus 4. Compare all these equation answers. Which one will conduct more heat? Say option D, dq by dt is more for option D, therefore D is the correct answer. The rod having radius 2 centimeter and length 0.5 meter is having more conductivity. Next question is SI unit of specific heat capacity. SI unit of specific heat capacity. We have studied in the first equation itself, Q is equal to ms into T2 minus T1, where T2 is the final temperature and T1 is the initial temperature of the system. M is the mass of the system and S is the specific heat of the system. Q is the amount of heat supplied to the system. Rearrange the equation to find the specific heat. S is equal to Q divided by M into change in temperature delta T. Now, to calculate the SI unit, to find the SI unit, say Q is measured in joule, M is measured in kg, delta T is the change in temperature. Temperature is measured in Kelvin. Therefore, the answer is joule per kg per Kelvin. Joule per kg per Kelvin is the correct answer. Since by definition specific heat is the amount of heat required to raise the temperature of 1 kg of substance by 1 Kelvin. Amount of heat required to raise the temperature of 1 kg of substance by 1 Kelvin. It is clear that joule per kg per Kelvin. A cup of tea cools from 65.5 degrees Celsius to 62.5 degrees Celsius in 1 minute. A cup of tea cools from 65.5 degrees Celsius to 62.5 degrees Celsius in 1 minute. At room temperature 22 degrees Celsius. How long it will take to cool from 46 degrees Celsius to 40 degrees Celsius? How long is the measure of time? 1 cup tea 65.5 ಡಿಗ್ರಿ ಸೆಲ್ಸಿಯಸ್ ಇಂದ 62.5 ಡಿಗ್ರಿ ಸೆಲ್ಸಿಯಸ್ಗೆ ರೆಡ್ಯೂಸ್ ಆಗಲಿಕ್ಕೆ 1 ನಿಮಿಷ ತಗೊಂಡ್ರೆ ಸೇಮ್ ಕಪ್ ಆಫ್ ಟೀ 40 ಡಿಗ್ರಿ ಸೆಲ್ಸಿಯಸ್ 46 ಇಂದ 40 ಡಿಗ್ರಿ ಸೆಲ್ಸಿಯಸ್ಗೆ ರೀಚ್ ಆಗಲಿಕ್ಕೆ ಎಷ್ಟು ಟೈಮ್ ತಗೊಳ್ತದೆ? We know that hot coffee becomes cooler faster in winter than summer. ಅಂದರೆ ಚಳಿಗಾಲದಲ್ಲಿ ಬೇಗ ಕೂಲ್ ಆಗ್ತದೆ, ಬೇಸಿಗೆಯಲ್ಲಿ ಕೂಲ್ ಆಗೋದು ಬಹಳ ನಿಧಾನ. ಯಾಕಂದರೆ temperature difference between system and surrounding is more in winter than in summer. This is we can explain using Newton's law of cooling. According to Newton's law of cooling, rate of cooling is proportional to temperature difference between system and surrounding. Or rate of cooling dq by dt is equal to minus k into T2 minus T1. Negative sign represents it is cooling. Temperature decreases. Here we can observe hot coffee. In the first case, similar to the previous problem, we can solve this. In the first case, temperature, initial temperature is of the system is 65.5 degrees Celsius and it reduces to 62.5 degrees Celsius. Therefore, rate of cooling dq by dt, we can calculate this as final temperature minus initial temperature divided by time taken. Time taken is 1 minute. This is equal to k minus k T2 minus T1. T2 is the temperature of the system. Since there are two different temperatures, take the average. Average temperature is 65.5 plus 62.5 divided by 2. That is 66 plus 62 by 2 or 64 degrees Celsius is average temperature. Minus temperature of the surrounding. Surrounding temperature is given, it is 22.5 degrees Celsius. 62 minus 65 minus 3 degrees Celsius is equal to minus k into 66 minus 22.5. 64 minus 22.5. This is 41.5. Take this as equation number 1. Similar to the previous case, Consider the second case. For the second case, temperature changes from 46 degree to 40 degree Celsius. Rate of cooling is final degree minus initial point divided by time taken is equal to minus K into temperature of the system. Temperature of the system is average temperature, that is 46 plus 40 divided by 2, which is equal to 43, minus temperature of the surrounding 22.5 degree. 46 minus 40, this is minus 6 by T is equal to minus K into 43 minus 22, 43 minus 22.5. 20.5, 21.5, we have two equations. Take the ratio. Equation 1 divided by equation 2 gives minus 3 divided by 1 divided by minus 6 by T is equal to minus K into 21.5 divided by cancel the common terms. We get this as minus, we can cancel 3 by 1 into T by 6 is equal to cancelling K 21, 41 divided by 21. Nearly 2, 1 2s or T by 2, for cross multiply we get T by 2 is equal to 41 divided by 21.5, cross multiply 83 divided by 21.5, 80 by 20, this is nearly equal to 4 seconds or 4 minutes. The answer is nearly equal to 4 minutes. Option A is the correct answer. Next, let us go to the next question. An aluminium sphere is dipped into water. Which of the following is true? Aluminium sphere is dipped into water. Which of the following is true? We have four options. Buoyancy will be less in water at 0 degree Celsius than water at 4 degree Celsius. Buoyancy will be more in water at 0 degree Celsius than water at 4 degree Celsius. Buoyancy in water at 0 degree Celsius will be same as that of water at 4 degree Celsius. Buoyancy will be more or less in water at 0 degree Celsius depending on the radius of the sphere at 4 degree Celsius. Here, when aluminum sphere is dipped in water, water exerts a force, upward force. This is called buoyant force. Buoyant force. Buoyant force is given by F is equal to rho V and G. Buoyant force is the upward force or upthrust is given by this equation, where rho is density of liquid, and V is volume of the sphere, volume of liquid dispersed, and G acceleration due to gravity. So it is given at two different temperatures, 0 degree Celsius and 4 degree Celsius. We know water has a special property, anomalous expansion of water. The volume of water is minimum at 4 degree Celsius. Volume of water is minimum at 4 degree Celsius. Density, we have the relation density is mass by volume. Since volume is minimum at 4 degree Celsius, the corresponding graph for density is maximum at 4 degree Celsius. If you cool the temperature below 4 degree Celsius, volume of water increases. Because of this special property of water, say buoyant force is minimum, V and G remains same, rho is maximum at 4 degree Celsius and rho is minimum at 0 degree Celsius. Rho is minimum at 0 degree Celsius, rho is maximum at 4 degree Celsius. Rho is maximum, V and G are constant, means buoyant force is maximum at 4 degree Celsius. Buoyancy is maximum at 4 degree Celsius. First option is correct. Buoyancy will be less in water at 0 degree Celsius than water at 4 degree Celsius. This is the correct answer. Next, move on to the next question, that is question on thermodynamics PV diagram. A thermodynamic system undergoes cyclic process ABC as shown in the diagram. The work done by the system per cycle. Here this is a complete cycle, reversible cycle. In this cycle, work done is given by area under the PV graph. Work done is given by area under PV graph. Now we have to calculate the area under PV graph. The shape of the graph is a triangle. Area of triangle is half into base into height. Base of a triangle is volume. Change in volume is from final volume is 10, initial volume is 5. Change in volume is 10 minus 5 mm cube. And height is nothing but pressure. Pressure changes from 100 Newton per meter square to 400 Newton per meter square. Therefore, final pressure minus initial pressure is 400 minus 100. This is half into 5 into 300, or this is cancelling and simplifying, we get this is 750 joule. Option A is correct. Next, 22. In adiabatic expansion of an ideal gas, the product of pressure and volume. Adiabatic expansion. Say it is given the process is adiabatic. The process is adiabatic. In adiabatic process, pressure, volume and temperature changes. It is a sudden process, or there is no heat exchange. Heat enters into the system. No heat enters into the system. dQ is 0. For an ideal gas, we have PV is equal to nRT. PV is equal to nRT for an ideal gas. And also from the first law of thermodynamics, dq is equal to du plus dw. Since dq is 0, du plus dw must be equal to 0 or du is equal to minus dw. But work done cannot be negative because work done is PdV. It is expansion. During expansion, volume increases. Therefore, dV is positive quantity or work done is a positive quantity. Work done is positive quantity because expansion. During expansion, volume increases. Change in volume is a positive quantity. Work done is a positive quantity. Therefore, only possibility is du is negative. du is change in internal energy. Internal energy decreases. That means final temperature is less than initial temperature. We have PV is equal to nRT. Since final temperature is less than initial temperature, N and R are constants for the given gas, or PV decreases as temperature decreases. The product of pressure and volume decreases. Option A is the correct answer. Let us move to the next question. A Carnot engine working between 300 Kelvin and 400 Kelvin has 800 joule of useful work. This question is based on Carnot's heat engine. The amount of heat energy supplied to the engine from the source. We have the equation for efficiency is, efficiency of Carnot heat engine is 1 minus T2 by T1. It is the ratio of amount of work done to amount of heat absorbed. W by Q1, which is equal to Q1 minus Q2 divided by Q1, or this is equal to 1 minus Q2 by Q1. This is also equal to 1 minus T2 by T1. Initial temperature of the source, say temperature of the sink, cold body is given 300 Kelvin. Temperature of the hot body is given 400 Kelvin. Amount of heat has useful work. Work done is given. Q1 minus Q2 is given. Amount of heat supplied from the source. You are asked to calculate Q1. Temperature of the cold body 300 Kelvin. Temperature of the hot body 400 Kelvin. Amount of work done Q1 minus Q2 is given 800 joule. Calculate Q1. Simplify this equation. Say Q1 minus Q2 by Q1 is equal to T1 minus T2 by T1. From this equation we can write like this. But Q1 minus Q2 is given 800 divided by Q1 is equal to T1 400, T2 300 divided by 400. Rearrange the equation and simplify this. 800 by Q1 is equal to 100 divided by 400, or this is 1/4. Cross multiply, we get Q1. Q1 is equal to 3200 joule. Amount of heat absorbed from the source is 3200 joule. Option B is the correct answer. Let us go to the next question. The next question is also on the Carnot's heat engine. For which combination of working temperature the efficiency of Carnot engine is least? Efficiency, we have the equation for efficiency 1 minus T2 by T1. Efficiency is 1 minus T2 by T1. Calculate efficiency for all these cases. For the first condition, efficiency is 1 minus T1, T2 is lower temperature, T1 is higher temperature. 1 minus, cancel this, 2 by 3, or this is equal to 1 by 3. 1 by 3 is 0.33. For the second case, efficiency is 1 minus T2. T2 is 20 Kelvin, T1 is 40 Kelvin, or this is 1 minus half, or this is equal to 0.5. For third case, efficiency is 1 minus T2 by T1. 60 by 80, 60 by 80 is 1 minus 3 by 4. 3 by 4, 1 minus 3 by 4 is equal to 0.25. For fourth case, calculate efficiency 1 minus 80 by 100. 80 by 100, 1 minus 8 by 10, (1 by 5), or this is equal to 0.2. Comparing all these options, efficiency is least for fourth option. Option D is the correct answer. Let us go to the next question again. Carnot's engine takes 300 calories of heat from a source. Heat absorbed by the source. You know, Carnot engine consists of working substance, source and sink. Source is maintained at hot body, temperature T1. Sink is a cold body, temperature T2. Working substance does some amount of work by absorbs Q1 amount of heat from the source, does some amount of work, rejects the remaining heat into the sink. This is the block diagram of Carnot's heat engine. Heat engine. Here, working substance absorbs Q1 amount of heat, Q1 300 calorie of heat from source. Source temperature is 500 Kelvin and rejects Q2 amount of heat to the sink, that is 150 calories to the sink. Temperature of the sink is, you are asked to calculate temperature of the sink. Efficiency, we have the equation for efficiency. Efficiency is 1 minus Q2 by Q1. This is also equal to 1 minus T2 by T1. 1 minus T2 by T1. 1 minus Q2. Q2 is 150 divided by 300 is equal to 1 minus 500 by T2. Simplify this. 150 by 300. 1 by 2 is equal to 500 by T2, or T2 is equal to 1000 Kelvin. Option D is the correct answer. Let us go to the next question. A sphere, a cube and a thin circular plate, all of same material and same mass, initially heated to same high temperature, are allowed to cool down under similar conditions. A sphere, cube and a thin circular plate. A sphere, cube and a thin circular plate have of same material, K is same, heated to initially same high temperature, temperature is same, allowed to cool under similar conditions. You know, heat transfers through three different modes. Heat transfer takes place by conduction, convection and radiation. Conduction is a mode of transfer of heat in solids without actual movement of particles. When one end of the rod is heated by a flame, the other end also gets hot. Temperature of the other end also increases. Here there is no bodily movement of particle from one end to another end, but heat transfer takes place. That is because of vibration of molecules. This method of transfer of heat without the movement of particles, ಇಲ್ಲಿ molecules move ಆಗದೆ heat transfer ಆಗುವ process ಅನ್ನು conduction ಅಂತ ಹೇಳ್ತೇವೆ. Convection is the second mode of transfer of heat. Convection ಅಲ್ಲಿ heat transfer ಆಗುವಾಗ molecules move ಆಗ್ತದೆ. Say for example, boiling water, ನೀರಿಗೆ ಬಿಸಿ ಮಾಡಿದಾಗ water molecules from the bottom, they absorb heat energy and they become less dense and they move to the top. ಮೇಲಿನ ಲೇಯರ್ ಫಸ್ಟ್ ಬಿಸಿ ಆಗ್ತದೆ. That is because of convection. Convection means mode of transfer of heat in liquids with the actual movement of molecules. And radiation, thermal radiation is another third mode of transfer of heat. Without radiation is a mode of transfer of heat. It takes place in vacuum also. Here convection ಮತ್ತು conduction ಆಗಲಿಕ್ಕೆ ಚಾನ್ಸಸ್ ಇಲ್ಲ. ಅದರಿಂದ heat transfer occurs through radiation. Temperature of the system and surrounding are same in all the three cases. Temperature of the system and surrounding are same in all the three cases because thermal conductivity is same and they are made of same material heated to same temperature. According to Newton's law of cooling, rate of cooling dq by dt is proportional to temperature difference between system and surrounding, or dq by dt is equal to minus k into temperature difference between system and surrounding. Here T1 is the temperature of the system, T is the temperature of the surrounding, K is a constant of proportionality. This constant of proportionality depends on nature of the material and area of the surface. Here nature of material is same in all this, temperature of system and surrounding also same. Therefore, depending on area of the material, surface area of the material, cooling rate of cooling is different. For the among these three, this plate has a larger area. Among the three, say sphere, cube and the thin plate, plate has a larger area. Therefore, cooling is faster for larger area. Plate will cool the fastest and sphere will the slowest. Option C is the correct answer. Let us go to the next question. Work done by the system in closed path ABCA. Work done by the okay. Say it is a PV diagram. Work done in a closed path is area under the graph. Area under the graph. Area of this triangle gives the amount of work done in this PV diagram. Area is given by half into base into height. Half base is volume, final volume minus initial volume. Height is nothing but pressure, final pressure minus initial pressure. Therefore, this is option is V2 minus V1 into P2 minus P1 divided by 2. Option C is the correct answer. Let us go to the next question. Temperature of the black body is increased by 50%, then percentage increase of radiation is approximately. Temperature of the black body. You know, black body is a body which absorbs all the radiations incident on it. Temperature is increased by 50%. Say T1 is the initial temperature of the black body. T2 is more than T1 by 50%. Say 150 T1. Then percentage increase of radiation is, energy of emitted radiation is given by fourth power of temperature. This equation is called Stefan's law. Stefan's law. According to Stefan's law, energy of emitted radiation is directly proportional to fourth power of temperature. E is proportional to T to the power 4 or E is equal to sigma T to the power 4. E1 is equal to sigma T1 to the power 4 and E2 is equal to sigma T2 to the power 4, where sigma is called Stefan's constant. Now E2 by E1, we can calculate this as sigma T to the power 4 divided by T1 to the power 4. Cancelling sigma, T2 is 150 times, 50% more than first body. T1 divided by T1 power raised to 4, or this is equal to 3 by 2 times cancelling T1, we get energy of emitted radiation is 3 by 2 times 3 by 2 power raised to 4. 3 by 2, 3 to the power 4 divided by 2 to the power 4, 3 to the power 4 is 81 divided by 16. 81 divided by 16. You are asked to calculate percentage increase in radiation is approximately. To calculate the percentage of increase in radiation, calculate E2 minus E1 by E1. E2 minus E1 by E1. E2 is the thermal radiation. (81 divided by 16 divided by 16). 81 minus 16 is calculating this, we get nearly 4 point something. Percentage increase E2 minus E1 divided by E1 into 100, that is 400. Percentage increase of radiation is 400%. Next we have assertion and reason. Read the following questions and choose. If both assertion and reason are true, reason is the correct explanation of assertion. Option B, both assertion and reason are true. Reason is not the correct explanation of the assertion. Assertion is true, but reason is false. Both assertion and reason are false. We have 4 options. The given assertion, Woolen clothes keep the body warm in winter. ಚಳಿಗಾಲದಲ್ಲಿ woolen clothes ನಮ್ಮನ್ನು ಬಿಸಿಯಾಗಿ ಇಟ್ಟಿರ್ತದೆ. The reason is air is bad conductor of heat. Assertion: woolen clothes keep the body warm in winter. Reason: air is bad conductor of heat. Both assertion and reason are true. Reason is the correct explanation of assertion. Woolen clothes ನಾವು ಚಳಿಗಾಲದಲ್ಲಿ ಯೂಸ್ ಮಾಡ್ತೇವೆ. Sweater, we use sweater during winter. ಚಳಿಗಾಲದಲ್ಲಿ woolen ನಮ್ಮನ್ನು ವಾರ್ಮ್ ಆಗಿಟ್ಟಿರ್ತದೆ. Assertion is true. Reason: air is bad conductor of heat. Is the reason true? Reason is not the correct explanation. Assertion is true but reason is false. Both assertion and reason are false. This is correct. Assertion is true because woolen clothes keep the body warm in winter, and reason is also true. Air is bad conductor of heat. Air does not conduct heat. Therefore, option A is the correct answer. Both assertion and reason are true. Reason is the correct explanation of assertion. Next, again, assertion: change of state is an example for isothermal state. Change of isothermal process. Change of state is an example for isothermal process. Isothermal: changes in pressure and volume takes place at constant temperature. What is an isothermal process? Changes in pressure and volume takes place at constant temperature is called isothermal process. During isothermal process, temperature remains constant, pressure and volume changes. Therefore, assertion is true. Change of state from solid to liquid occurs at melting point of solid. The reason is change of state from solid to liquid occurs. Solid ಇಂದ ಲಿಕ್ವಿಡ್ಗೆ ಸಬ್ಸ್ಟೆನ್ಸ್ ಚೇಂಜ್ ಆಗಬೇಕು. ಮೆಲ್ಟಿಂಗ್ ಆಫ್ ಐಸ್. ಐಸ್ ಮೆಲ್ಟ್ ಆಗಿ ಲಿಕ್ವಿಡ್ ಆಗುವಾಗ is there any change of temperature? There is no change in temperature. There is Q is equal to ml. Latent heat. We use the energy as a latent heat. This energy is used to change the state of a substance and not the rise of temperature. Change of state from liquid to solid occurs at its melting point of solid. Pressure and volume changes, temperature remains same. This is called amount of heat supplied is called latent heat. Supplied energy is used to change the state of a substance. This is true. Change of state from liquid to gas. Again, if you raise the temperature from 0 degrees Celsius to 100 degrees Celsius, temperature up to 100 degrees Celsius, temperature goes on, changes, increases. At 100 degrees Celsius, there is change of state and there is no change of temperature. Liquid changes into vapor at 100 degrees Celsius. 100 degrees Celsius ಅಲ್ಲಿ ಮತ್ತೆ temperature change ಆಗದೆ volume and pressure changes. Pressure and volume changes at constant temperature, that is isothermal process. Thus, there is no change of temperature during the change of state. This is also true. This is also true. Therefore, option A is the right answer. Both assertion and reason are true, and reason is the correct explanation of assertion. This completes all the 30 questions, and thank you. Students, in ಕೆಲವೇ ದಿನಗಳಿವೆ CET ಎಕ್ಸಾಮ್ಗೆ. do well in the exam. Wish you all the best. ಥಿಯರಿಯಲ್ಲಿ ಒಳ್ಳೆ ಮಾರ್ಕ್ಸ್ ತಗೊಂಡ ಎಲ್ಲ ಮಕ್ಕಳಿಗೂ ಹಾರ್ದಿಕ ಶುಭಾಶಯಗಳು. ಬೇಗ ಬಂದಿದ್ದೆಲ್ಲ ಊಟ ಮಾಡಿದ್ದೆ ಒಂದು ಆಯಿತು.